All
Go
right.
ahead.
Cool. Yeah, so hey everyone, I'm Mark. I'm a senior over at Pitzer College, and today I'm going to be talking about Legionnaire's disease and using some mathematical modeling to kind of understand it. And okay, so starting off, I'm going to talk about a little bit of background and motivation, and then talk about the model and some of our preliminary results, and then some of our ongoing work and future direction. So Legionnaires was first reported in 1976. As we can see by this incidence rate, it's only continued to grow in incidence and rate and reporting over the last couple of years. And we noticed this like slight dip in trend, but this is due to around the COVID time where reporting wasn't as great. And something to be concerned is that alongside this increase in incidence rate, we also have a increase in mortality rate. So this is definitely something to be concerned about as the rate of reporting continues to increase, the rate of mortality is also increasing. And so to define what Legionnaires actually is, it's a type of pneumonia, which is like a type of lung infection. And this is caused by this bacteria called Legionella. And this is generally caused most frequently by this L. pneumophila serogroup 1, which was again first identified in 1977. And so the general spread of Legionnaires is through like inhaling these water droplets in the air that have the bacteria inside. And some like most common cases is things like public sources of water where like a water source is supplying for example, like a hospital or like a hot apartment complex or generally just potable water. So like showering water, sink water, things like that. And so a lot of the complications that come through Legionnaire's disease are things like respiratory failure, we have things like shock, multi-organ failure, brain sequelae. And another problem with Legionnaires is that it's generally pretty underdiagnosed and underreported. It's something that's pretty hard to detect and something that's like undetectable through X-rays. And it's also hard to distinguish from other types of pneumonia. And so while antibiotics do exist, it's kind of hard to diagnose it in the first place and thus difficult to diagnose the right type of antibiotics. And so there's also no vaccine. And so, since it's so hard to diagnose and it's kind of difficult to treat, we kind of wanted to think of a different way to reduce Legionnaires or the difficulty of dealing with Legionnaires. And that idea is just to actually try to reduce the risk of the Legionella growth in the environment. And so, this is kind of the goal of our little research group of me, Christina, Li Hong, and we currently have another undergraduate student working at Harvey Mudd. And our kind of goal is to better understand Legionnaires using math modeling. And we want to kind of continue to build up on our model and make it more robust and also incorporate other factors that might relate to Legionnaires. So as we continue to learn more about the disease and get more data on it, we can hopefully make some improvements in our model. And so moving on to the model that we built and some results that we have. This is our model. It's somewhat simple, but since this is the first mathematical model in Legionnaires, we wanted to make it try to capture like basic dynamics of a closed population. And this is kind of building off of a lot of other environmentally transmitted disease models like Burley ulcers and cholera, where we have this SEIRB model, where we have the susceptible, exposed, infected, the recovered, and the B, the pathogen class in the environment. And translating this into a more mathematical model where we have our state variables that are ordinary differential equations, we have these equations as shown. And we see that here in our susceptible and exposed environments, we have this B over H sub B plus B term multiplied by our beta, the transmission rate. And so what this is really doing is we're scaling the likelihood of actually getting Legionnaires after being interacting with the bacteria in the environment. So that's what this B over H sub B plus B scaling term is. And then we also wanted to note in the pathogen class, we have this logistic decay alongside this dB plus times B. And since again there isn't much data on Legionnaires and it's pretty underreported, we had to do a lot of es parameter estimation to get our parameters for our model. And to do this, we just used fmincon inside of MATLAB, and we just took the L2 norm of the difference between the actual data and our simulated data. And to make this a little bit more efficient and to make it more accurate, we wanted to parallelize this process using multi-start. And what this is doing is essentially we're starting at a bunch of different points, and we're going to run this fmincon process at all of these points. And so the data that we were specifically using to and that we wanted to capture was this outbreak back in 2001 in Murcia. And this is the largest outbreak of Legionnaires to date. And so from literature, we found that our gamma, which is the average incubation period, and our lambda, which is the average recovery period, was this 1/6 and 1/14. So we didn't have to do any parameter estimation for that. And since this is also such a small outbreak or short in time frame, we assume that this pi, mu, and delta, which is the natural birth rate, the natural death rate, and the disease-induced mortality rate, we set to 0. And we changed this a little bit in our model just to see what would happen, but it was pretty negligible in the difference that it made. And so this is the simulated data that we got from fitting our model. The orange dots you see in the bottom right, this is the cumulative infected population. And the orange dots is the actual data set that we had. And while we weren't able to get a perfect fit, since this was a very small time population, we were able to generally capture like the basic dynamics. And this is the rest of our simulations for our SEI R and B. And so after we did some parameter estimation, we kind of wanted to understand, since we did estimate our parameters, we wanted to know which parameters might be more important in their sensitivity of the infected class. And we were able to find using LHS and PRCC that the statistically significant parameters were this beta transmission rate, lambda and gamma, the recovery period and incubation period, and this H sub B, which is the half saturation constant, were the most statistically significant. And this is kind of interesting because as we saw before, the beta and B over H sub B plus B terms were heavily paired together as it was kind of a scaling term. And so it's interesting that the beta, the transmission rate, has such a high sensitivity to the infected class, while the H sub B has a very low sensitivity. And so this is something that we're pretty interested in. And furthermore, we have this lambda and gamma, which since we didn't estimate, it's not too important for us to keep studying it, but it is interesting how much these will affect our infected population. And so after that, we've built our model and we kind of understand our parameters a little bit better. We wanted to run some optimal control to see like how our system would fare under a type of control. And so our main idea was that since Legionella can actually survive at these temperature ranges between 25 and 42 degrees Celsius, we kind of can assume that humans might be the most common cause for Legionella outbreaks, as we generate like some artificial sources of water that can actually have Legionella survive. And this is kind of the case also in literature searches. So our idea was to filter the water that individuals actually interact with as our control method. And so here's our idea is this U vector, which is the percentage of cleaned water. And we incorporate this into our previous model by just adding this 1 minus UT term in our susceptible and exposed populations. And so using this, we can make our objective functional that we want to minimize. This is the cost of basically, you can think of the red as the cost of doing nothing. It's the cost if we let the disease go on and the outbreak to continue, what is going to cost us? And the orange term being what's going to cost us to actually sanitize the water and run our control. And so we use the forward backward sweep method to find the optimal U such that we can minimize this objective functional. And after running some numerical simulations, this is what we have. On the left, this is the base model I showed before. This is our fitted model based on our data set. And on the right, we have our results from optimal control. And this tells us that we actually want to run our control for the entire 15-day period. As we see in the exposed, over here on our base model at 15 days, we're at about 130 exposed. But when we're actually running our control at 15 days, we drop down to about 70. And you can see this is a general trend for the infected population as well. And so this is something we're pretty happy about as we managed to get some significant management results. And after that, we also wanted to understand how changing some variables around might affect um, our control problem. And so our first idea was to see how varying costs would affect our control problem, as realistically, if we were actually able to implement this, we would have some cost that would be involved. And so in our variations, a high variation would be if we had a super high cost of running the control, and a low variation would be a low cost. And what we have kind of makes sense. If we have a super high cost of control, we're not going to run it. And as we can see at the flat zero at the control, we're not going to run it. And when we don't run it, we're going to have a high exposed and high infected population. And this is the opposite. If we have a very low cost, we're going to want to run it the entire time and thus flatten out our exposed and infected populations. And since we, again, estimated our parameters and beta was the most significant estimated parameter, we also wanted to understand how, if we had some different values of beta, how it would affect our system as well. And so if we have a super high value of beta, then we're going to run the control the entire time. If we have a low cost or low transmission rate beta, then we're not going to run the control. And again, this is reflected. If we run a control the entire time, the curve will flatten. And if we're not running the control, the curve will be allowed to grow. And so generally, just to summarize what we've done, we made this novel mathematical model. Again, this is the first real mathematical model for Legionnaires, and we fitted it to this specific outbreak where we identified our statistically significant parameters, these beta, lambda, gamma, and h sub b. And then we used some optimal control theory and figured out what the control is going to do for our system and saw how it might affect our control if we changed some things like the cost of sanitization and the transmission rate. And something we're also more interested in doing is understanding the environment class B, as we currently don't have much data on it and there's not much existing literature, but we want to understand how we might incorporate it better into our model. And so some of our ongoing work and future work is this kind of age and gender-based model. So we have data that shows that the male to female ratio is actually pretty significant. And there's also a increase in incidence rate based on your age. And so this is something that I'm currently working on and implementing this and incorporating it into our model. And something else that we also considered is these health disparities. So in the social determinants of health, there's a lot of things like economic stability, education, health and healthcare, and more of these things that actually impact disease. And this is not just limited to Legionnaires, but more specifically for Legionnaires, a clear telltale sign is this incidence rate by race in this graphic right here, where we can see for different races, there's a significant difference in incidence rate. And so thank you so much for listening. Please let me know if you have any questions. Thank you.
Awesome. Thank you so much. So as you said, we will open it up to questions. And we've got about 10 minutes until we got to head out. So
I just want to start by saying thank you for a beautiful talk, very well presented, very clear diagrams, and thank you for pointing out relevant technical details and everything throughout. It's very clear. Thank you so much.
Thank you.
What are you most excited about on working? You mentioned a little bit of current and ongoing work. What do you think is the most exciting direction that you're working on right now?
Yeah, I think yeah, well, right now what I'm working on is specifically like this age-based model. So we're kind of interested in incorporating these age categories. And I particularly am pretty interested in doing PDEs. So I think having like a age-based model makes much sense for a PDE model. Like if we do a continuous age like relation. So I think that's what I'm particularly interested in. But there's a lot of other things that can be done with Legionnaires. I think there's a lot of like seasonality things, a lot of spatial things. So I think those are definitely interesting directions to go with this.
Thank you so much.
Yeah, sure. Is there something in the chat? Okay, cool.
Any more questions or anything? Again, great job. This was very nice, nicely presented. And thank you so much for joining us. We're excited to have you.
Thank you for letting me give a talk here.
Of course. Let me stop the recording. I forgot it was on.